Jai Hind all of you. I'm Dr. Rahul Bansal from the Ajay Kumar Garg Engineering College, Gajwad. So this one is the next video lecture for the electron devices KC 301. So let us start. So in this video lecture, we will be discussing about the compensation and the space charge neutrality, right? So we know that in the N-type semiconductor or P-type semiconductor that are called as the extrinsic semiconductor material, right? So this the process of compensation of semiconductor behavior is to alter if at all this Na denotes the number of this acceptor ion, right, and this Nd denotes the number of donor ion, right. So if at all number of acceptor ion is much larger than this donor ion, then this is called as the compensated P-type semiconductor, right. And if at all number of acceptor ion is less than that the number of donor ion, then it is called as the N-type semiconductor material, right. If Na is equal to Nd, that is number of acceptor ion is equal to number of donor ion, in this case it is said to be perfectly compensated, right. In this case the material will be highly resistive, right. It will have the high resistivity, right. So if you see compensation in an N-type semiconductor material in which number of donor ion is much greater than number of acceptor ion. So in this type of like materials, we will have, like, if you consider this as like conduction band and this as valence band, right. So in the acceptor ion will be in case of like a discrete energy level is created just below the conduction band, right. So this discrete energy level here it is denoted by Ed, right, and this energy level is called as the donor ion energy level. Next is acceptor ion energy level, it is represented by Ea here, right. So this is near to the valence band actually, right. So if I talk about the donor ion N-type semiconductor material, in this case electron will be the majority charge carriers and the holes will be the minority charge carriers, right. So each electron will be like bonded with the positively charged ion, that is the acceptor ion, right. And each hole in case of P-type semiconductor in which holes are the majority charge carriers, each hole will be bonded with the negatively charged ion, or you can say this donor type ion, right. So according to the space charge neutrality, if the material if we want that the material is to be remain this electrostatically neutral, the sum of the positively charged, that is hole and the ionized donor atom, it must balance the sum of the negatively charged, that is electron and the ionized acceptor atom. If we combine both, then they should be match. Then that is N0 plus Na, it should be equal to P0 plus Nd, right. It means that sum of the positive charges which is obtained from the holes and the ionized donor atom, right, and some of the negative charges, that is electron and the ionized acceptor atom, they will be like equal. So this is called as the this leads to the space charge neutrality, okay. And in the intrinsic semiconductor is itself is electrostatically neutral. So what we can say? We can say that the doping atom that we add are also neutral, right. And the above equation, if you want to rewrite this as in the thermal equilibrium state, so it can be like written as N naught plus Na is equal to P naught plus Nd. Right. So this is the equation that we have like got after computing that. Right. Also, we know from the mass action law, that is N naught into P naught is equal to Ni square. So this we already know from the mass action law, right? So what we can say? We can say that this N naught is equal to Ni square divided by P naught, which will give me P naught is equal to Ni square divided by N naught. These both are like equal. These both are, we can obtain the value of N naught, that is the electron concentration at the equilibrium state, and the P naught, that is hole concentration at the equilibrium state, we can compute from this mass action law. So if I consider this as equation 1, I can put the value of P naught, that is equal to Ni square divided by N naught, from this mass action law to this equation. What we will get is, we will get N naught plus Na is equal to Ni square divided by N naught plus Nd. Right. So we can take this Nd to the left hand side, right, and so this will give me this equation, which is in the form of quadratic equation. So we can solve this equation using the standard formula, that is, if at all your equation is ax square plus bx plus c equal to 0. So your x will be equal to minus b plus minus root b square minus 4ac divided by 2a. So using this standard mathematical equation, we can find out the value of N naught, right? So N naught is coming out to be, this is the value of B, that is Nd minus Na. So Nd minus Na divided by 2, right? Root B square, that is Nd minus Na divided by 2 whole square plus Ni square. So this is the mathematical equation for N naught. Now if I put N naught equal to Ni square divided by P naught in this equation, in the first equation, so we will get the value of P naught, that is the hole concentration, right? So hole concentration is computed to be P naught equal to Na minus Nd divided by 2 plus root of Na minus Nd divided by 2 whole square plus Ni square. So this is the mathematical expression that we have got for the electron concentration and the hole concentration at the equilibrium state, right? So you must note these two equations. These are very crucial for your examination purpose. Now come to the next topic, that is the drift of the carriers, electron movement under the electric field force. So this is very crucial and this is very important for your examination point of view, right? So in any material, if I say in any solid, right, all the charge carriers moves randomly. Ideally they move this randomly. Even if I provide some thermal energy, right, so at the thermal equilibrium state, the motion of the charge carriers, say it is like electron, okay, it will be random. Suppose that if I consider this material consists of these electrons, so if I apply the thermal energy, so they will move here and there. Some electron will be moving in the left direction, some electron will be moving from the to the right direction, right? So such that this movement will be random due to the thermal energy. Okay, so this is due to the scattering of the lattice vibration, right, and the impurity and the defect, right? So due to the random scattering, no net motion of the group of the n electron will be there. Why? So why it is so? Why I am making this statement? If you consider electron is moving, first electron, jth electron, say it is jth electron, is moving in this direction, right? Correspondingly, at the same time, another ith electron will be moving in the opposite direction, so that the net motion of the group of n electron over any period of time, if I observe, it will be like 0. So net current will be equal to 0 in this case, right? So why it is so? It is due to the electron movement. Some electron are moving like in this direction, okay. At the same time, some many electrons, or you can say equal number of electrons, will be moving in the opposite direction. It means that the net current density will be equal to 0, right? So they will not contribute toward the conductivity. So if I apply the electric field, say it is like Ex means we are applying in the x direction electric field, right? So if I apply the electric field in the x direction, so each electron will experience a net force of minus q into Ex. That is, it will be in the reverse direction, right? And this force may be insufficient to align the random, right? It may be sufficient or it may be insufficient, right? So the path of the individual electron, if I say like the effect of this will lead to the electron resultant net motion of the group in the minus x direction, right? So if I say electric field is applied in this direction, initially electron are having some random motion like this. Some electron are moving in this direction. Correspondingly, if I say jth electron is moving in this direction, correspondingly ith electron will be moving in this direction, right? If I say kth electron is moving in this direction, correspondingly this electron will be moving in the opposite direction, right? So if I apply the electric field, all the electron will be aligned, right? If I say like electric field is in this direction, right? Now the net velocity will be in the opposite direction, right? So electron movement will be in this direction because this net force is in the opposite direction. That is, velocity will be equal to, we have discussed this in the previous video lecture, that is, velocity will be given by minus nu n into electric field, where this mu n denotes the mobility, right? So through this way we can compute the velocity also. What is the velocity? If we know the value of electric field, right? So if I say like we have the electric field, right, and we have some like momentum for the electrons, for the nth electrons, for the n electrons, right? So we can compute the force also. So force is like given by, the force will be like equal, that is a minus n into q into Ex, right, which is due to this electric field. It will be equal to dp upon dx, that is momentum of the electron, right? So if I say like this is equation 1, so what does this equation signifies? It says that the constant acceleration of the electron in the minus x direction, right? So this is not the case because net acceleration of is counterbalancing the steady state by the deceleration of the electron. Okay, so this is due to the net change of momentum when collision are included. It must be like 0, right? So all the group of the electron moves with the constant velocity if I apply the electric field in this case, right? So if I say the mean time between the collision or the scattering is like t, right? And the probability of the collision in the time interval t dt is dt upon t. Therefore, the differential change in the momentum to collision in the time dt is like given by p upon px upon n, which is equal to minus q into t multiplied by ex, right? The average net velocity, that is also called as like drift velocity of the electron in the negative x direction, is given by this px divided by mn asterisk, which is equal to minus q into t upon mn asterisk into e, right? Which is given by this equation, right? Now we can also compute the current density. So current density is equal to Gx is equal to minus q into n into Vx, right? So and the velocity and the drift velocity equation, that is Jx is equal to n into q square multiplied by t divided by mn asterisk into e x, right? So this is the final equation for the current density in the x direction. Now J is actually equal to sigma into x, where this sigma denotes the conductivity. So conductivity is given by n into q square multiplied by t divided by mn asterisk, where this mn asterisk is actually the effective mass of electron, which is higher than that of the rest mass of the electron, right? Next is sigma is equal to q into n into mu n, where this mu n is called as a mobility, electron mobility. Mobility describes the how ease, right, with which the electron drift in the material, how fast the electron is moving in the material, right? So this is given by the drift velocity, and how is the electron is moving in the material is it is given by the electron mobility, right? So drift current density is equal to minus q into mu n into n plus mu p into p multiplied by e, that is e into s, that is the electric field. So this is the net equation for the drift current, current density, right? So thank you all of you. This was all for this video. In the next video lecture, we will discuss about the next topic, right? Thank you.